All right, so here we are. This is 129S, Securing Web Applications. And we talked about the basics of web application security last time, and we're just going to go through a couple more chapters here. And hopefully you have started doing your projects, including the ones from Portswigger. And I see, good morning. All right, and so let's take a look at those slides, which I should have open, but I may have trouble reaching on my unusual setup here. Well, open it. Doesn't open. All right. Where is it? Supposedly open. Ah, here it is. Okay, good. Just the problem is Zoom puts other junk on top of Windows, so I can't find them. All right. So we're down to core defense mechanisms, and I'm going to make this as big as I can. All right. All right. So the problem with, as we talked about last time, the fundamental problem with securing the web is that users are sending up all this data, and the data can include special characters and commands that are misunderstood. So the first thing you can do is limit what users can get to, so they can't get to the supposedly sensitive parts of the app. Then you can try to filter out the special characters out of the input so they don't put in exploits. And you can try to do things like lock people out after multiple guesses of a password to frustrate them. And you can have administrative monitoring where you have things like alerts and log reviews to notice when people are doing bad things. These are general defense elements. So users authenticate. The process of authentication is first you have identification where you claim to be somebody. Then you have authentication where you prove it with knowledge of something like a password. And then the app has to somehow keep track of who you are as you traverse through the pages in the app. And that's session management, usually done with a cookie. And then there's access control, where the app has restricted areas where it checks to see who you are before letting you in there. And so that's authentication. Like I say, username and password is the cheapest and most common. It's much better to have multi-stage or multi-factor login, where you have to have more than just a name and a password. There are smart cards, client certificates, these RSA tokens, and many other ways to do it. The problem is, as soon as you have a login and something like a password, your users are going to lose their passwords, and you have to have some kind of password recovery. And that turns out to often be the very weakest spot. Recovering a lost password usually relies on something very simple, like the name of your first car or something, which is in fact pretty easy to find out. So it tends to lead to problems. So a login will ask you for something like a username and password to log in. And so the usernames are usually predictable, simply based on your name. And a lot of people just use the same simple passwords everywhere. The top 10 passwords are things like 1, 2, 3, 4, 5, 6. So an enormous number of users will use foolish passwords all the time. And there are many ways to make mistakes. So you have something like a cookie that keeps track of the fact that you're logged in. And you might have your sessions expire, although most modern websites don't seem to ever expire it because they don't want to make you type your password again on a phone. And so the tokens are sometimes predictable. This is not that common anymore because it's so dangerous. If I look at my cookie and it's just like a number, like 1003, I can just add another number to it and get somebody else's cookie and get in their account. So that happens occasionally, but it's a serious problem, and people will fix that when you report it. But what's more common is that the tokens are handled in a foolish way, so there's a way to steal them. For example, a way to find the supposedly random contents of it elsewhere on a page. So once you're in, you have to figure out who somebody is and then decide whether to give them an access denied page or let them into there. And user input is another issue. When you give someone a form for something like first name, last name, email, then they will often make mistakes. So you can usually with client-side JavaScript, you restrict what they type in here, but that's not really the best procedure because you can't be sure that really happened. If you use a tool like Burp, you can change the contents of the packets before they leave your network adapter, and you can change them to send forbidden characters here. So you can use JavaScript validation just to not waste any server time on customers that make errors, but you cannot trust it and believe that it's really happened. So if your first name only has 4 characters here, you cannot assume at the server that what they send will only have 4 characters. So people send all kinds of data up there, including arbitrary text like blog posts, and there are HTTP headers in the HTTP request, which we'll look at a little later. So there's a lot of fields coming from the user's browser, and all those are intrinsically under the user's control, and they could all contain commands, malicious code, special characters, and so on. So the most common, but the least effective method to stop attacks is blacklisting, where you try to list all the bad things and remove it. This is how antivirus typically works. It just has lists of all the known viruses, and it tries to remove it. So you see here, they block the word select because you might be using that in a SQL injection. And so if I just change the case of the characters, it might not match. And I've got more here. I try to block these things. You can just change them in ways that won't match the filter, but will still have the same effect. There's a lot of tricks. You can add comments in the middle of a SQL command. You can put a null byte at the start, which will be accepted by the web server and let the data through, but it might be stopped by the web application firewall or the block. Now I see a question here. Not random. Do I mean pseudo-random? Yes, yes. Cookies are generated by cryptographic secure functions. Not necessarily, not at all. The cookies are generated by sort of automated development platforms, and often they make terrible mistakes. Another thing that is quite common is you write some kind of random number generator, and then you use it for multiple purposes until there's some purpose I can see, like it's used for a challenge token on a page where I can see it in the source page, or it's used, for example, in a password reset email. This happened to Facebook. Somebody got, I think, $5,000 or $10,000 for reporting it to Facebook. If you forgot your password and got a password reset email, there'd be this URL with a random number in it. And they found that that random number was the same as a random number somewhere else on your page, like in the URL of a photograph on your page. So they could go to somebody else's page and predict the URL of a password reset and perform a password reset for them. That's the kind of thing that happens. So there's also the issue of predictable random numbers, but what I hear more commonly is not that the random number is predictable, but that somewhere the random number is exposed. And that's why another general category of vulnerabilities that people think of as low priority is information disclosure vulnerabilities, where you just see something about the internal workings of a page. And by itself, it's not a big problem, but it can lead to a big problem if that value turns out to be useful. And so blocking all the bad stuff is not very effective because it's very hard to think of all the versions of a bad thing. This is just a challenge for the ingenuity of the hacker to find a way to express their command without using the characters you're blocking. What's much better is whitelisting, where you just have a list of acceptable good values and you don't take anything except what's on the list of acceptable good values. But it isn't always possible, but where practical, it's much more secure. So there's another very dangerous and very common practice on the web called sanitization, where you get input from the user that has a problem. And what you do is just filter out the bad characters and then use the remaining characters. Now, this is very common, but not a very good idea because it just means attackers can try sneaking stuff through. But anyway, that happens a lot. And we'll talk about this. So safe data handling is the general property of finding ways to process data that cannot be fooled by malicious data that's set up. And all right, it's not as easy as it sounds, but all right, there's some malicious input that looks like valid input. For example, if I change an account number to somebody else's account number, there's nothing malicious about it. It doesn't have bad characters, and yet it's going to do something. It's going to be referring to an account that I haven't logged in. So the access control list ought to prevent me from messing with that, but people may forget they may assume that just presence on some kind of account management page indicates authorization. And we'll see quite a few examples of that as we go ahead. All right, so here's the problem with simple input validation. The idea, you have data coming in is untrusted and the server-side app is trusted, but your app may very well change several processing steps together, and almost all modern apps do. They will pass it to a web server and then to a PHP engine and then to a SQL server and then to something else. And each one of those processing stages has a different list of weaknesses and a different list of bad characters. So the bad characters that are accepted at one stage will not be safe at another stage. So you have to define trust boundaries. Each server needs to define what the inside of my server is and what are the ways data comes in and how do I check all the data coming in to make sure it doesn't contain attacks, and how do I check all the data going out to make sure it doesn't contain attacks for wherever the next stage is. So that's what you need to do if you want to be safe. And the problem with this, of course, you have a setup like this. You go to a login form, it goes to an application server, then it goes to a SQL server, then it goes over to a SOAP server. And so each one of these devices would have to consider the input and output. The problem is the person that maintains your SQL server probably doesn't understand SOAP. And even worse, your company keeps growing and expanding. So they might add a database function to something that didn't used to have a database function. So the existing code here that was secure at one time is no longer secure. And that's what leads to so many problems, because everybody keeps growing and expanding and merging so that the environment of your application changes. And this is really the root of almost all security problems. There's another example of it in the world of Microsoft Windows. Microsoft Windows has a bunch of ways to reuse code. So you can take code that was originally written on a non-network machine to run inside one application, and you can share it with other processes, and then you can share it over the internet with other things. So code that was originally running in a very limited environment ends up being reused in a much wider environment. And that, of course, is one of the many ways you end up with security problems. Of course, the point is you also end up with making more money from your code. You can sell it on a larger market. People can easily buy code and use it in different situations. So the rapid pace of innovation and marketing that makes the web so valuable is also what makes it so insecure. So here's a SOAP request. SOAP requests look like normal HTTP requests. It's a post. And then down here, instead of having HTML, they have XML, which just sends some data up. So this has some header stuff that is pretty much boilerplate. And then down here, it sends a quotation name Microsoft. That's what it's sending. So here's an example of this boundary validation. You have username and password, so you check that there's no special characters and length and so on. Then you go to a SQL query, and you might escape dangerous characters like apostrophes there. I see a question here. What does encode XML meta characters? The meta characters in XML are less than and greater than. And so you would encode them as ampersand LT semicolon and ampersand GT semicolon. And then they could pass to somewhere where they might be used, but they wouldn't be understood as meta characters in the context of XML. We're going to get here later, but for example, suppose I control this quotation. If I put in normal letters in this quotation, it will be understood as a quotation. But if I could put in greater than and less than signs in this quotation, I could insert XML tags into the data that came from me, and then I could override functions here, like authentication and so on. We'll do that later in the course. Very good question. It's very much like SQL injection. XML has injection too. Anyway, so when you succeed, you pass data through a SOAP service, and now you can have XML meta characters in there. So you encode them as HTML, so they will not be interpreted as active ingredients in the XML. Then you send data back, and again, HTML encoded. This is the way you make things safe. You have to consider what your app takes in and filter out the dangerous things, and what it sends out should also be filtered so that it does not have unexpected results on the next step. So here's filtering problems. If I use a grep type filter that just looks for this string and removes it, I could just send this. It's the beginning of the script tag, then a whole script tag, then another. When my single pass of filtering happens, it will delete this, leaving a script left over. So these are the many tricks where a simple attempt to block things doesn't really work. For example, I want to stop people from doing directory traversal and putting in .. that will move out of a directory into the directories above it. So I remove .. then I remove .. because that also works. So all an attacker has to do is send them in this order. There is no .. but after you remove the .. what remains is a .. and I've managed to sneak it through. So canonicalization is another big issue. So we were just talking about this a few minutes ago when I asked about the encoding of meta characters. An apostrophe is %27. You know, you can put these characters in a browser. For example, if you go here and you want to have a space in a URL, you can type a space and then go there. Let's see if I can get it to take it. Stop messing with me, a space. All right, and then enter. All right, and notice what happened. There is no page like that, but notice what it did up here in the URL bar. It put in %20 where my space was. 20 is 32 in hexadecimal, and that's the code for a space. You can put in these %20 characters. Any character you want can be expressed that way, % and then 2 digits. And it is the HTML encoding. So let me get back to my... all right, so apostrophe is 27, % is 25. So if you want to block apostrophes, to block SQL injection, you might filter %27. But early versions of IIS, Microsoft's web server, encoded the URL twice. So you could put in %25, 27, and that would become %27 because %25 is the % sign. So this, when doubly decoded, turned into an apostrophe. Microsoft made that mistake. And the problem is this is easier to make this mistake than you think because some of your appliances might be encoding or decoding characters, like your web application firewall. And quite a few of the attacks are based on understanding that the defenses are written in one language and the actual application is written in a different language. So you can filter something through that the defense will not see, but the actual web app will still see. So you've got errors, you should have logs, and we'll talk about how you react to attacks. So if you have an error, if you do not handle the error messages, you'll just see garbage like this. A few years ago, I was testing web pages for security, and I tested the National Republican Party's page. And I just put an apostrophe in the URL, and the entire page turned into screaming red ASP error messages because it was running on a Microsoft server. And I decided to leave it alone because it was not in good shape at all. But this is the point. If you see automatically generated code like this is not only unprofessional looking and bad from a marketing point of view, but it's also dangerous because I can often see source code. I can see what versions of things you're running. Your customer should never see this. If there's an error, you should just have a page that says, I'm sorry, I can't find that page. Please go here for our search engine or go here for our help desk. You know, you should show them a polished presentation. This kind of internal technical data should not be visible to the end user. All right, and so you should have logs. You should be logging events like login success, failure, password changes, credit card payments, other important things. And now for the highest security, you could say you should log every client request in full, but that will slow down your server and burden it. I had to do this on one of my servers. I had a SQL injection page, which we'll be using later in the projects. And a guy kept injecting stuff beyond what I thought was possible. And I asked him, how'd you do that? And he said, you're so smart, figure it out. So I finally had to turn on Apache forensic logging so I could see every request to find out what he was doing. And that was interesting to learn about, but it does slow down your web server. You cannot handle as many customers per second that way. So your logs will contain times, IP addresses, usernames, and if they log entire requests, they're going to have cookies and possibly even passwords and other sensitive data. So you have to protect the log itself. If you take our classes in Splunk, which is a very good product, Splunk lets you view log files and it has a whole permission structure so you can restrict who's allowed to see those logs because the logs often have sensitive data in them. And there was an entertaining vulnerability a while ago where LMOS servers were often open to the world. I think Toyota had an open LMOS server. So you could go to the Toyota website, and if you put an apostrophe in the URL, it would log that as an error right in the publicly accessible log viewer. That was what, and so if you could send someone a malformed URL on their site, it would put their cookie in a publicly visible spot. So there's the kind of thing that happens pretty often. Let's see, this is kind of, yeah, the kind of information disclosure, exactly. Yeah. All right. So if you do have weird things happening, then you ought to be alerting the administrator. And this is one of the many things you can do with an intrusion detection system or a system like Splunk that monitors log files. You can notice a lot of funds transfers to the same account, places where hidden data has been modified that was not supposed to be modified by the end user. These are things that ought to alert people, or perhaps even just automatically ban that person off your website for a day or something. And you'll hear this in almost every chapter of this book. They say, here's things you can do to prevent this. Notice when people are sending funny data and block them. Don't let people try many, many attacks until one gets through. All right. And so web app firewalls are very common because they help you achieve compliance. If you want to achieve, say, PCI compliance, you have to have one. So you buy a box, you connect it in line with your web server, you pay for it to be automatically updated, and it blocks known attacks. But like antivirus, it's a very weak defense. They're pretty easy to sneak through, but they do stop vulnerability scanners, which is what they're designed for. They're designed to make the vulnerability scanner certify that you're good enough. And they're better than nothing, but you can't trust them too much. All right. What's better is to actually check to make sure that your parameters are valid on your business. And that would be a customized control, more powerful than a generic web application firewall that isn't really designed for your business, and it can only stop the most obvious attacks. So attackers probe, they typically run a vulnerability scanner or a burp or a script. They send many, many requests that are very similar, trying different punctuation marks and stuff to get in. So there's plenty of ways to automatically defend yourself from that. Products like Bro, now called Zeek, can be configured to just block people after a certain number of attack packets. You can also just slow down the response to each one. These are things you can do to prevent people from just running automated scans. Your management interface. Somewhere in your website, there's a management interface. Typically, if you're using something like WordPress or the military uses PHP Nuke, you have an administrator page where you can, add more posts and change user passwords and such. And the management interface is a high-value interface, and you might want to put this behind two-factor authentication or VPN, something like that, so it's harder to get to. So if they attack the administration panel, they might be able to guess the password, find some kind of weakness in the authentication. If you don't keep things updated, there are often known vulnerabilities that let you in the administrator page. So let's take a look at some cahoots. Let me see if let me get them going here. All right. Here. All right. This is chapter 2. There we are. Good. Good. Okay. Good. I have a place to put the answers. Okay. I'm managing with my system a little messed up. Okay, good. All right. We got 24 people, so probably a few more will be still coming. Oops. It is 1:28. Okay. I'll give it a few more seconds. All right. Good, it's working. All right. What happens when you log in? Okay, that's authentication. You give it a password to prove that you really are somebody. All right. How does a website remember who you are? That's session management. All right. If you write code that can't be fooled by malicious data, what's that? All right. That's called safe data handling. These other techniques are not very strong. There are possible attempts to do it, but the goal here is safe data handling. And what process removes malicious portions of input and then uses the remaining portion? Okay, that's sanitization. All right. So the winners. I know who that is. And they'll have to tell me who that is if they want their points. And same thing here. All right. All right. Let's go back to here. And we're done with this one. And there's another one. Should be another one. All right. $29S. All right. Somehow it's hosed me. 129S. No, that's not it. That should be it. There we go. And there we go. All right. Good. I see some names. Okay, I'll record them. Clickers. And okay, good. I got those names. Good. Let me set this back to everyone. And all right, so now we're going to talk about how HTTP works. HTTP is the fundamental protocol of the web, and as I mentioned before, it was never designed to do what we're doing with it. The point is it's connectionless. It was designed to be efficient, so a very weak server can serve a lot of clients. So you get one request from a client, you answer it, and then you're done. It has no state. It doesn't remember who you are. It is a single transaction, like you pay money and you get a product. So you send a request, and the request is just a line of plain text that looks like this. Get the name of something you're trying to get, then a version of HTTP, and then you have other header lines that might be there. Modern versions of HTTP require that you always have the host. The rest of this stuff is pretty much optional. So, all right, this in a URL, you can have the name of a folder or file, and then you can have a question mark and some parameters. Those are parameters which are not part of the file name of the file stored on the server. They're extra parameters set along which might be used by a script on the server. All right, the referrer, which by the way is spelled wrong. It should have 2 R's here, but it doesn't. That's the URL that the request originated from, but it is not verified by anything. It is like the from address in an email or the identifier of who you are in a telephone call. Those things can all be spoofed. I can claim to come from anywhere. So anybody that trusts the referrer as proof that they came from a certain place shouldn't. All right. And then you can have cookies like this. Many cookies, a whole series of things separated by semicolons are all in the form value equals data. So underscore GA is this. And most cookies just look like long random numbers like this. That's the best practice. You could put real usernames or passwords or something in a cookie, but it's not a good idea because they're not handled very safely. Referrer misspelling, yes, was a mistake for the original HTTP request for comment. This entire thing is defined by these requests for comments that go through organizations like the IEEE, and then they post on the web, and after a while they just become standards. And the original standard had it spelled that way. It's sort of like a mistake in a law. There is no enforcement of HTTP standards, but people pretty much obey them because if you don't, then your product will not interoperate well with other products. Microsoft used to be a huge offender. Internet Explorer totally broke all the standards because they owned like 99% of the desktop. So they didn't care what the standards were. But now Microsoft has reformed and they pretty much obey the standards because now they're just mixed into the other fish. They're not the dominant player anymore. So after you send an HTTP request, the server will reply with a response. And the first line tells you whether it worked. 200 means it understood your request and here's the answer. Other things like 404 means something went wrong. There's some header information here that tells you what version the server is and the date and such. And then down here, you'll have the answer. Here's some data it's sending. All right. And so here's another HTTP response. This one has some set cookie parameters. Those are what's going to put the cookie. Now the cookie is remembered by your browser. It was not part of the original HTTP protocol. It was an invention of Netscape. They wanted some way to have authenticated pages like email, so they invented this idea of your browser storing a cookie on your machine. And the cookie is just a text file with these values. Name equals value. It remembers what site it came from, and then it has an expiration date. So the cookie is stored, and that's how it identifies you. And it has the security measure of the same origin policy, for better or worse. It remembers the domain that set this cookie, and it will only send that cookie to a request to the same domain. It will automatically send that cookie to every request that goes to that domain from now on, so the domain can check to see if you have logged in, and it remembers who you are. And now you have a session of sorts. But the session is remembered in a sort of strange way. The cookie is defined by the server, set in your browser, and then every time you go back to the page, your browser sends the cookie up again, and the server can recognize you. That means you have a chance to modify that session variable. That's why a proper session variable is like this, a long random number. I could not easily guess somebody else's number. If I could just get right into their account. All right, and so here's other things like expires, and you can also set a pragma field to tell it not to store the response in its cache. Otherwise, it might save not only the cookie, but it might save images from the page and so on, so that it can redisplay that page more quickly. And here's the message body. And this, the data type here is defined up here in the content type. So this is JavaScript data in UTF-8 character set. You define up here what kind of data is going to be seen down there. The most common method is get. This is what you normally use when browsing the web. You get a page, you see the page. This retrieves resources. You can also send parameters. You can bookmark the whole URL. That's why anything in the query string, part of the URL, is not considered safe because it can be put in a log on the server and it's stored in the URL. So let me just go and demonstrate that to make that clear. If I go to, say, Google, and I search for like frog, then it adds parameters up here, google.com/search, and then it has a bunch of junk there. And one of the things it'll have up there is Q equals frog. Looks like they've added all sorts of extra junk on mine, so I can't find it. But in a normal situation, you just see it right there. But all those parameters would be stored if I stored this as a favorite. So nothing up here should be considered safe, even if it's sent by HTTPS. Now, the HTTPS at the start of this URL means that it will be encrypted on the web and nobody can see it except Google. But once it's there, it might be stored in a log. Anything up here in the query string is not considered a very secure place to send data up. All right. So a post parameter is better. A post has the right place to send data up. You can send parameters on a post request, and if you try to refresh a page or go back to a page with a post request, your browser will warn you that you're probably performing an action twice, like logging in or buying something. If you refresh the page, you might be buying two of them, which is not the case with GET requests. All right. And so a head returns just the header from the server and not the body, so it's not commonly used, but you can use it. Options shows what methods are allowed. These are the methods. Get and post are the most common method. Sometimes people use put and others, but most of the time, most of your web traffic is get and post. And this is what URLs look like. You have a protocol, then a host name, something.com typically, and possibly a port number. Then you have a path, a series of folders. Then you have a file name. Then you have question mark, parameter equal value. So if I look at my web page here, let's go to, this Kahoot page will do. So the protocol is missing. It's probably HTTPS. It doesn't always show you that. Then it's got always the : //. Here's the host name, create.kahoot.it, because it's Italian. IT is the end of the host name. Then it has the path, which is /cahoots/favorites. So it has a couple of folder names. It doesn't have a file name. So this will go for some default file name like index.html or something. And it doesn't have any parameters. Now, as I mentioned before, here's the Google page. So it's got the HTTPS, the name of the server, and then a search, and then a question mark, and here's some parameters. So that's the structure of a uniform resource locator. And if you don't specify the port, it will assume 80 for HTTP and 443 for HTTPS, and that's almost always the case. Almost nobody uses a port because normal users aren't going to type it in. Refer or miss, yeah, that's right, there's an old question there. All right, then there's RESTful URLs, just to keep you good and confused. When I said that Kahoot parameter, a Kahoot thing there was a folder name, I was guessing. When you look at Kahoot, and here it has favorites, I assume that's a folder name, but that could be a parameter. You can write your web server to take this information here and interpret it as a parameter instead of a folder name, which is downright rude and confusing, but that's the way it is. That's called representational state transfer. So a normal request would look like this. You'd have the name of a page, and then you'd have parameters, make equals forward, model equals Pinto. But in REST, you could just put search forward Pinto, and the web server would just be told in its configuration to interpret this is a folder name, but that is a parameter, and that is another parameter. These browser extensions like HTTPS only, how do they work? Well, the HTTPS only browser extension just prevents you from using HTTP. So every time you go to a URL beginning with HTTP, it just changes it to HTTPS. That was popular a few years ago when there were a lot of HTTP websites that hadn't yet upgraded to HTTPS. Pretty much everybody is now upgraded to HTTPS. I don't think it would add the HTTP only to the cookie because that's another issue. We'll talk about it later, but the point of the HTTP only flag is to prevent you from stealing the cookie with JavaScript. That does not mean it only goes over HTTPS. That would be the secure flag. Could I modify all cookies to add that pragma field to help prevent stuff getting cached? I think you can actually turn off caching globally in your browser. I think it's an option in there, although I haven't done it, but if you want to, then it won't have any extra copies of images and style sheets and such that it would otherwise cache. Good. So let's take a look at another Kahoot. We're up to chapter 3, Kahoot A, which should be somewhere in my list here. There we go. Good. All right, I guess that's it. All right, what's the get? That's the method, also called the verb. Get and post are the most common verbs or methods. What method requires user confirmation when you click back? That's post, because post usually performs some kind of action that you might not want to perform twice. What parameters are in bookmarks? The query string, anything you see in the address bar of the browser goes in the bookmark, also called a favorite. All right, which of these is REST? Okay, that's RESTful. Here's the normal query structure. And these are other ones you might see. This is XML and this is JSON. Many different ways to express the same information. That's the RESTful one. All right. All right, Darlene. All right, and Clicker, I know who that is. And Kunal looks like a real name. Good. All right. So I know who the winners are. And let's go on. So, yes, it's 2:57. You've been here for about an hour. Let's take a 10-minute break, then I can process this video. So we'll pick up at 3:10. And I'm not going to leave right away, but I am going to stop the video and process it.